Okay. Hi, everybody. This is Miss A again, coming to you with another stats live stream. Hopefully, some of you will see this video. So we're going to be talking about another very big topic for the AP exam that we went over back in Unit 6, specifically Lesson 6.3. Right, yes, sorry, my previous stream, which was 2 days ago, I talked a bit about the binomial distribution. So the binomial distribution is the distribution that we use when we're talking about what's the probability of getting X successes out of N trials. So let's say, like, if I want to, so for instance, the example we used was around COVID patients. If we have 50 patients and a certain average probability of fatality due to COVID-19, how can we estimate the probability of getting nobody out of the 50 dying, or 2 out of the 50 dying, right? Or any specific number. So the ones that we looked at were specifically around what's the probability that 1 out of 50 will die? What's the probability that 5 or more out of the 50 will die? And it kind of came down to the formula that we used, which, again, please ask if there's anything you'd like to know about that formula. It basically comes down to, what's the probability of success? And how many successes do you have? What's the probability of failure? And how many of those failures do you expect to have? And then how many different combinations will lead to that particular number of successes? So, like, how many different ways of picking one person out of 50 are there? How many different ways of picking 5 people out of 50 are there? And those numbers grow very, very quickly. We use that formula to talk about, estimating the number of potential fatalities. I used the calculator, right? And on the Inspire, right, we use the binomial CDF function. We put in the number of trials, the probability of success, the sort of the lower bound and the upper bound. So this was when we were looking specifically at, some number of successes greater than a certain value, or greater than or equal to in this case. When we went to do the expectation, we were talking about, this is going to just be what's the probability of success times the number of trials. So say if we've got 50 patients, there's a 5% chance of death. The estimate comes out to 2.5, which, again, this is an average, which is where we get that 0.5 from, right? We're not anticipating half a death. That would be kind of a strange measurement. So today we're going to talk about, or I'm going to talk, I guess, about a bit more of a kind of specialized topic when it comes to this, right? So let's look at the problem, right? So now let's assume there is a 2% probability of contracting COVID-19 every time we leave the house. Again, this is a number I pulled out. Please don't go quoting this number to anybody, right? I'm just using this number 2% as a starting point, right? It's a nice round number, and it's kind of sufficiently small to be realistic, but not anyway, right? This is just an example. We're illustrating, right? We'll leave the actual number gathering to the professionals, right? They can tell us what this probability looks like. But of course, that probability is going to be very, very different from everybody, right? So when you see a problem like this, that 2% there is this 2% here is really just talking about, this is an average. This is a very kind of first pass kind of value where you don't know anything more specific about the person, you don't know where they live, right? Me here in New York City, numbers are probably going to be very different than someone who lives upstate or someone who lives out in the middle of nowhere in Wyoming. You know, it takes no account of the precautions I may or may not be taking, how many people I may or may not live with. So when you see a 2% like that, or when you see the news quoting some like one single number, remember that like that's how you're supposed to take it. Like this is a population-wide value, and you should only be using this value in the absence of more specific information, right? Or like information that takes into account more details, right? This is a very high level. If you know nothing else, this 2% number represents the average kind of thing. So, right, we have this very broad statistic, or this very broad probability, and so this is every time we leave the house. So, essentially, right, when we think about this problem, right, there is something binomial-ish about this. We're talking about a certain number of trials, right? Like, what's the probability that I can go out 20 times before contracting the virus? So we've got 20 trials. We've got a certain probability, right? So, right, if we need to remember our conditions, the conditions were binary outcomes, independent trials, which we have. Again, we're assuming let's say if I go out today and I don't catch COVID, it's not going to change the probability that I do or don't catch it if I were to go out tomorrow. So the trials are independent of each other, at least up until the point that, say, I start developing symptoms and I can't go out anymore. But at that point, you know, we don't really need probability. The probability that I would get COVID is 100% because I would have it. So number of trials is fixed, right? We're talking about going out 20 times. And so we're saying, right, like what we're expecting here is to go out 20 times, and then we catch it. So that's the important part here, right? When we're talking about before contracting the virus. So in this case, right, this fits the binomial in a certain way, but we're not talking ever a situation about like multiple successes, right? I'm not asking the question of like, what's the chance that I catch COVID 3 times out of these 20, right? It's not necessarily a question that doesn't make sense, right? We could phrase it in terms of exposure. What's the likelihood that I would be exposed 3 times out of the 20, right? That could be a binomial problem. But in this case, we're assuming that I go out 20 times and then I catch the virus. So like on the 20th time, that's when I catch it. So basically we're thinking here of like 19 successes and 1 failure. So that's basically the kind of situation that we're going to be taking a look at here. So again, if you guys want to follow along, I'm just getting the page number here. If you have a copy of the Practice of Statistics, again, it's lesson 6.3 on geometric variables. Those start on page 422 in the 6th edition. If you know you're not in my class and you're still watching this video, if it's the 5th edition, it might be a somewhat different number. But basically we're saying, right, managed to go out 19 times totally successfully. 20th time, bam, there we go, we caught it. So this is what we're going to call a geometric situation rather than a binomial one, even though like if you were to treat this as a binomial, it would not be incorrect, right? You're talking about a situation where there's 19 failures, 1 success, and So we've got 19 failures, 1 success, and the number of ways of getting that is really just 1. 19 failures followed by 1 success. There's only one combination of events that looks like that. So geometric situations actually get nice and simple compared, at least like if we're looking at its formula compared to the binomial, right? We do not need this, kind of funny combination term right here, right? That term is unnecessary. Because there's only one combination of events that gets this. For our case, the geometric distribution is, the formula is going to look like, so the probability of having X successes before X trials before first failure Excuse me. I am still very new at the whole streaming biz, so I need to remember to turn off my phone when I do this. Okay. And so basically if we're saying, right, 20 trials, right? We went out 20 times before getting sick. That would mean that we had 19 failures and 1 success, because that 20th time, that's when we caught it. So the way this is going to look is 1 minus p, right? That's the probability of failure, to the x power times p. And that's just to the first power because there's only 1 success. Or sorry, this should be x minus 1. So if we were to go back to this problem of what's the probability that we go out 20 times before contracting the virus, right? We would say the probability that x equals 20 is going to be, right, 1 minus 0.02 to the 19 times 0.02. Again, that's going to be a, if we have a 2% chance of success, that means we have a 98% chance of failure. So now let's bring up the calculator. I'm still getting used to this new TI software that they have, I guess, somewhat generously allowed us to use for free during these remote learning months. Again, if you have not had a chance to get the TI Inspire software, please send me an email, leave me a message. I can help you out with that. Okay, so still loading. Next time, I promise I'll be smart and pre-plan this and put this up. While we're waiting for the software, how is everybody doing? Who is watching this? Maybe you're watching this today. Maybe you're watching this a while from now. How are you doing? How are you dealing with COVID? I am still stuck in this room for now. I have my lovely assistant, BB, off camera, who just did not take kindly to being woken up there. What are we all doing to stay sane? I know I've been kind of going a little bit old school. I've been playing a lot of Magic the Gathering online. It's like a card game, but there's an online version. I've been playing it since I was in middle school. Okay, great. I think we should... Okay, cool. There it is. There's the calculator. So on the calculator, going to take a look at, well, what is 0.98? Ooh. All right, yep. Let's remember to add calculator page. Ooh. And menu. Oops. Let's do Control plus page. Okay, so our problem was 0.98 to the 19th power, and then we'll multiply that times 0.02. And our answer is there is about a 1.4% probability of this happening. Let's take off the calculator, sorry, I think my software is bugging out a little bit. There we go. All right, now it's playing a little nicer. So we said this is going to be approximately 0.014. Okay. So this would be the probability of that. But I don't know, let's actually maybe take a look a little bit further at this. What might it look like if we were to look at the distribution of these of the probability density functions? So let's take a look. Okay, let's turn on the calculator. All right, so let us open up a graphing page. And let's add, all right, so we're gonna go to menu, graph entry, sequence. I do believe it should be sequence. All right, so basically this is going to come, we are going to go to the menu, we are going to pick all right, so let's not do it that way. All right, so let's just go ahead and type this in directly. So we're going to say this is like so hard to do on screen. I am not used to doing this on screen like so. Let's try this one over again. All right, so we're going to pick from here. Let's open this up. Stats, distributions, and we're going to pick the geometric PDF because we want to do this at each value, right? That's kind of what I want to show you guys here. Okay. We're going to have to zoom this in a weird way, but let's do this first. All right, graph entry. I'm going to do a sequence. And we are going to, let's not go up to 99. We don't need to stress this thing out too much. We'll go up to like 25. And here, again, we're going to pick the geometric PDF. And so we're going to give it the number of trials, which in this case, we're just going to use the regular, since the variable here is n, we're going to go ahead and say n, comma, and the probability is 0.02. Okay, and so now let's zoom. Actually, here, let's do the window. Our x minimum can, That's fine. That's fine. All right, let's look at the maximum. X max, let's say, should be about 0.5. Oops, no, that should be 25, and then Y max should be 0.5. Oops, did I do this wrong? I think I might have done these backwards. Let's try it the other way around. There it is. All right, so let's just do zoom, fit. This will fit the data for us. So it kind of looks like this. Let's take a look at the table. Might be useful here. All right, so if you see, right, the highest likelihood comes at like 1 time. So this is just like individual, right? What's the probability for exactly this number? For it's, let's say, going out exactly 10 times. So each individual probability is actually really, really low. What if we kind of changed it around a little bit and instead we were looking at this as more of a range of values, right? Let's say, like, what's the likelihood that I can take 10 or more trips before getting sick? Or what's the or like flip it around, what's the probability that I get sick in fewer than 10 trips? So let's kind of take a look at that calculation, right? That's going to be where we use a CDF instead. So let's see what happens when we do when we use the CDF. I'm going to change up so let's change the sequence that we're using. So instead of PDF, this is going to be CDF. And I believe in this case, yeah, I think I did this one wrong. Oh, I think I did this one okay. Here, let's take this guy out. Let's remove that table, and let's change the zoom again. And there we go. So say if we look at the CDF of this, it almost kind of looks linear. But basically we're which in a certain way makes sense, right? We really are like kind of each time just sort of adding a similar amount to this overall probability. It does kind of flatten out a little bit as it goes up, right? As we get closer and closer to like 100% chance. So let's go back. Let's take a look at the table again and see what these numbers look like. So again, right, we start with that 2% chance of getting sick after 1 time out. We kind of crossed the 10% threshold around 6 trips outside. We crossed 20% around 12. We crossed 50% right around 34 or 35 trips out. And so basically at that point, right, they basically have like a 50-50 chance of getting it in less than 34 or more than 34 tries. So that's kind of our break-even point. Anything past that, you're more likely to get sick than to not get sick. But again, right, this is an overall, like, this is something that we're kind of predicting in advance. If you've already made those 20 trips and you're asking what's the chance that I get sick on my next trip out, that's just 2%, right? Like, your chance on any given trip outside is 2%. But if we're starting here and we're projecting into the future and saying, what's our probability of getting sick in 20, after 20 times, but not getting sick before then, right? That's where the geometric distribution helps us. But it's not really helpful for tracking like day to day, moment to moment kind of things, right? This is really us kind of projecting in advance based on a trend. Wow, this calculator window looks like it's wigging out a little bit. All right, let's put you to sleep. Okay, let's bring the iPad back. Okay, so I kind of wanted to introduce let's add another problem in here. Did I lose the iPad? I think I lost the iPad. Restart this. Screen mirroring. And we're back. Okay, so I'm going to introduce a new question here, right? So asking ourselves, like, what is the probability of never mind. This stream's already running a bit long, so let me just answer the second question and finish this up for today. On average, how many trips outside would you expect a random person to be able to take before they get infected? So basically, like, we're asking ourselves, like, in a sense, like, how many times, again, this comes down to that expectation, right? We're basically talking about where is the mean of this distribution, like, more or less, where do we hit that 50-50 probability? And so, like, the number of trips we would expect before their first infection is going to be 1 over the 1 over the probability of failure, or sorry, the probability of success. So if we have a 0.02 probability of success, then the expectation is going to be 1 over 0.02, which is going to come out to, when we do this, 1 over 0.02 should give us 50. Sorry, I don't know why that took so long to for those words to come out of my mouth, but this should come down to 50 trips. So this is basically our expectation for the number of times that we'll go out before being infected. Obviously, that is not going to be true for everybody, right? This is going to be for this is us projecting for a totally random person in the absence of any other real clarifying information or specifying information. But we should, with this little minimal amount of information, still be able to make some kind of a prediction. Anyway, sorry, I've gone a bit long already. I've been trying to want to keep these to under about a half hour. So thank you all for joining me. If you are joining me, whether that is now, whether that is later, please let me know if you have any questions or anything you'd like me to go over, either like here on YouTube or in Google Classroom. So this is Miss A signing off. Hope you guys have a lovely rest of your day.